Welcome to the Lab Cafe, where some of Nepal's favorite caffeinated beverages are getting ready to be scientifically analyzed. But first, let's meet the menu.
The aroma of tradition. I miss the bold brew, the classic city scene. I've been waking people up across Nepal with a strong body and a strong legacy. Did someone say 2.4% caffeine? You're welcome.
Namaste, I'm Miss Jet Leaf, the elegant infusion. I'm light, graceful, antioxidant-rich, and yes, up to 4.3% caffeine. Who says healthy can be strong?
Yo, I'm the Bean Baron. Medium roast, full flavor, zero drama. I drink a mellow jolt with my 1.52% caffeine. Quality over chaos, my friends.
Let's go. I'm rocket, short, fast, furious, finely ground. I hit the HPLC detector at 2.66 minutes flat. Pure precision in powder form.
As you can see, each drink has its own vibe, not just in taste, but in personality too. But beyond all the drama and fun, there's a real question we need to ask. How can we actually measure how much caffeine is in them in a clear and accurate way? In this video, I will presenting about a study titled as simple HPLC method for the determination of caffeine content in tea and coffee. This study was published in the Journal of Food Science and Technology Nepal in 2016, and it was conducted by a researcher named Shrestha, Pokhtar, Rijal, and Wright. The reason of why the researcher doing this study because in Nepal, tea and coffee are not just beverage; they are cultural staples consumed every day by people of all ages. However, while caffeine offers benefits like increased alertness, reduced fatigue, and improved concentration, the excessive or unregulated intake can lead to health concerns such as anxiety, insomnia, and high blood pressure. Moreover, in a consumer market where different brand and processing methods are used, there can be a huge variation in caffeine level from one product to another. For regulatory body industry alike, knowing the exact caffeine content is essential to meet safety standards, label accuracy, and public trust. Due to that, this study stepped in to solve the problem by using an analytical method known as HPLC.
So, what is HPLC? HPLC stands for High Performance Liquid Chromatography. It is a powerful technique used to separate, identify, and measure each component in a mixture, especially useful when the target substance, like caffeine, is present in small amounts. In the HPLC setup, the sample is dissolved in a liquid solvent and then pumped through a column filled with a special solid material. Different compounds in the sample interact with this material in different ways, and so they travel through the column at different speeds. When caffeine reaches the detector, it creates a distinct signal at a specific time, called the retention time, which was found to be around 2.66 minutes in this study. By measuring the strength of the signal, we can determine exactly how much caffeine is present in the sample. The primary goal of this study was to develop a simple, fast, and validated HPLC method to determine caffeine content in commercial tea and coffee products available in Kathmandu and Kaski districts in Nepal. There was a clear need for this because prior to this study, there was no straightforward local method that could be adapted for routine testing. In addition, national food safety standards in Nepal require that tea should contain at least 2% caffeine and coffee should contain at least 1% caffeine on a dry basis. Ensuring product meets this threshold is essential for consumer protection and compliance with the Department of Food Technology and Quality Control.
Next is sample collection. A total of 12 CTC tea samples, 7 green tea samples, 8 medium roasted coffee beans, and 3 coffee powder samples were collected from Kathmandu and Kaski districts in Nepal. All samples were stored at room temperature throughout the analysis to maintain their natural condition. For the sample preparation, the moisture content of all tea and coffee samples were determined by following the AOAC 2005 method. This step is to ensure that the caffeine results can be expressed accurately on a dry weight basis. The samples were then ground into a uniform fine powder with a particle size of approximately 300 plus or minus 50 microns to facilitate consistent extraction. 0.3 grams of the powder sample was weighed into a 250 ml conical flask and diluted with 200 ml of distilled water. The mixture was heated in a water bath at 100 degrees Celsius for 30 minutes to extract caffeine into the aqueous phase. After cooling to room temperature, the solution was filtered using Wolfman No. 1 filter paper to remove particulate matter. Then 1 ml of filtrate was pipetted into 10 ml volumetric flask and diluted and using HPLC grade water. Finally, the solution was passed through a 0.2 micrometer microfilter to remove any residual fine particles and then transferred into HPLC vials for chromatographic analysis. Moving on, the HPLC analysis was performed under these conditions. Column C18 reverse phase, mobile phase 60% water and 40% methanol. The flow rate are 1 ml per minute. Column temperature at 40 degrees Celsius. Detector is UV at 275 nanometer. Injection volume at 10 ml microliters. Next stage is method validation, where it is validated according to the ICH guidelines, which to ensure that the analytical method is reliable, accurate, and precise. First, linearity and range were tested to confirm that the instrument response increases proportionally with caffeine concentration. This was done by analyzing 5 standard solutions ranging from 2 to 10 ppm and plotting a calibration curve. Secondly, precision. It was evaluated by measuring the method's consistency. This involved 6 repeated injections of a 10 ppm standard solution under intraday and interday conditions. Thirdly, sensitivity. It was determined by calculating the limit of detection and limit of quantification using low concentration caffeine samples and monitoring the signal to noise ratio. Finally, accuracy, which was confirmed through recovery tests, where known amounts of caffeine were added to decaffeinated the tea samples. Moving on to the findings, this study tested 5 different caffeine concentrations from 2 to 10 ppm to represent the levels found in tea and coffee. Each sample was injected into the HPLC using 10 microliters and measured the signal or peak area. They repeated each test 3 times and used the average result. The graph showed a strong linear relationship, meaning as caffeine concentration increased, the signal also increased. The R-square value was 0.9928, which means the method is very accurate and consistent within this range.
And next, let's begin with the finding from the caffeine standard solution. This chromatogram represents the analysis of the 2 ppm pure caffeine standard using HPLC and UV detections at 275 nanometer. As we can see, there's a sharp and distinct peak appearing exactly at 2.66 minutes. This peaks, it indicates to pure caffeine and establish the retention time that we can use as a reference point. The significance of this peak is critical, as it works as a marker for identify caffeine in unknown sample. Any peaks in the sample that appears at exact time is very likely to be caffeine. This confirmation of retention time ensures accuracy when we compare the tea sample chromatogram next. And now, moving on to the tea sample analysis. In this chromatogram, we can see that there's a prominent peak also at 2.16 minutes, which matches the retention time from the caffeine standard. This clearly indicates the presence of caffeine in the tea sample. Furthermore, the area under this peak plays a crucial role in quantifying the caffeine content using the calibration curve derived from the standard solution of the non-concentration. We can calculate how much caffeine is present in the tea. This matches in retention time along with quantitative data from the peak area, which confirm the successful identification and determination of caffeine in the tea.
Now let's take a look at the precision of HPLC method. This table shows the intraday repeatability where the same 10 ppm caffeine standard was tested 6 times on the same day. The retention time for caffeine remained consistent, averaging around 2.648 minutes, and the area value were also 7. The relative standard deviation (RSD) for both retention time and peak area was less than 2%, which is considered excellent for analytical method. This result confirmed that the method gives consistent and repeatable measurement within the same. Next, this table shows the inter-day repeatability where the same 10 ppm standard was analyzed over different days. Again, same with the previous slide, the average retention time was consistent, but this time at around 2.690 minutes, and the area value stay within an acceptable range. The percentage of RSD for both parameters remains low, which indicates that the method is not only precise on the same day but also stable and reproducible over time. Together, both intra and inter-day tests demonstrate that HPLC method is highly reliable and precise for determining caffeine content.
For the next findings, we conducted a recovery test using blend or decaffeinated tea sample. This sample was spiked with unknown amounts of caffeine, which is 1.27 mg, 2.52 mg, and 3.81 mg. As shown in the table, the HPLC method was able to recover 97.6%, 98.8%, and 98.4% of the added caffeine respectively. This means that the method was successfully recovered over 97% of the caffeine in all cases. This high recovery percentage confirms that the method is both accurate and reliable, and that it is not affected by the sample matrix. This supports its suitability for the next findings. We conducted a recovery test using blend or decaffeinated tea sample. This sample was spiked with unknown amounts of caffeine, which is 1.27 mg, 2.52 mg, and 3.81 mg. As shown in the table, the HPLC method was able to recover 97.6%. So, this table shows the actual caffeine content on a dry basis, measured in various tea and coffee samples. All the samples tested meet Nepal's minimum caffeine standard, at least 2% for tea and 1% for coffee. Among all the samples, green tea showed the highest caffeine level, even higher than CTCT and coffee beans. Also, the presence of standard deviation values across the data shows that the measurements were consistent and reliable. This confirms that the HPLC method used is suitable for accurate caffeine analysis across different beverage types.
And now, let's begin by looking at the importance of this study. Firstly, we develop and validate a simple high-performance liquid chromatography, or we call as HPLC method, specifically for a lot of different samples. This method stands out because it is a cost-effective, highly accurate, and also reliable. That makes it suitable for routine analysis by labs and regulatory bodies. Beyond that, this method helps in monitoring caffeine levels so accurate, which is crucial for protecting consumers from potential overexposures and mislabeled product. Most importantly, this research also contributes to building a technical capacity here in Nepal. It encourages the adoption of advanced techniques like HPLC in local laboratory that push the standard of food testing forward. To conclude, this research successfully developed a simple HPLC method for determining caffeine and content in both tea and coffee. This method was highly accurate and sensitive, with a low detection limit of just 0.2 ppm and a rapid analysis time under 3 minutes for each sample. It gives a high recovery rate of 97% and could effectively separate caffeine from other compounds that exist in it. All tested products met Nepalese standards, and based on this promising result, the Central Food Laboratory has recommended this method for regular use. This study clearly demonstrates how specific innovation can be applied directly to improve public health and ensure food quality, and also enhance food safety practice in Nepal, which also we can use here in our own country, which is Malaysia.